concentrated in the first 18 there. So you can see here where the different variables are declared to be in shared memory. The ones that are the green, say the multiple expansions, are in shared memory. The spherical harmonics, these are calculated also in shared memory. The local expansions are in the registers. And all of this is explained in detail in the GPU gems. Of course, in this environment here, I can't go into details also. We're running soon out of time. But this is the way the code is available to you to read. And then if you look at the second part here, this is where the actual multiple expansions are calculated. And there's some things which are calculated on the fly using a recurrence relation. On the CPU, you will probably have some sort of list. You don't calculate them on the fly, but on the GPU, you want to avoid some movements of data. And these are the functions that calculate these things in this GPU kernel. I see that my time is soon running out, so let me just jump to some of the results. This is the FMM on GPU and versus CPU, FMM and tree code. The blue line is on CPU, and the green line, the NVIDIA color, is represents the GPU one. So you can see for the direct all pairs evaluation, of course, a very good speed up here, 300-fold speed up. I think that is measured. I need to have a particular end that is measured. Let's see. Well, I'm sorry, I can't find it very quickly, so I'm just going to assume that it's at the end of it's with one of these big ones, right? It's a million or it's got to be one of these in the end. It's got to be explained in my in the chapter, but I'm afraid I don't have it handy, so I could tell you exactly what end that speed up refers to. But what I want you to focus in is that we have a 300-fold speed up for the all pairs, which is the most parallel process. For the tree code, we have a 100-fold speed up, and for the fast multiple method, a 30-fold speed up. So you may say, oh, you know, that's not great, that's just 30-fold speed up. But remember, we're already using an order n algorithm, which is quite complicated, okay? And it's not bad, actually, when you're moving from an order n square problem to an order n, from an order n square algorithm to an order n. You've already obtained dramatic improvements. And so a 30-fold speed up over the order n algorithm is pretty good. And here, this is the GPU, right? The green one. So you can see that below n 10 to the 4, the overheads of tree construction on the GPU are messing up your performance. So obviously on the GPU, the crossover points move to higher n. The crossover points between the different algorithms move to higher n. So you have a crossover point here at, say, I think here, this crossover point between where the fast multiple method starts becoming faster than the direct, 10 to the let's see, 1, 2, 3, 3,000, right? Here. Then the crossover point is about 20,000 on the GPU. It moves forward. Okay, that's what I wanted to point out to you. These are actual performance measures for the different kernels. The P2P obviously performs very well. You can see in the order of 300 gigaflops for the P2P because it's very parallel. And also note that the multiple 2-particle is also performs quite well on the GPU. The multiple 2 local, and here is the explanation why we get only a 30-fold speed up. The multiple 2 local is giving 100 gigaflops in this code. Now let me point out to you that the code that's presented on the GPU gems, we try to kind of simplify it to the maximum so that for the purposes of explaining it better, so it's kind of more pedagogical reasons, and it's not the best that you could hope for. We don't claim these are the greatest speedups. We do have other codes that work better, but they were much more messy, and we wanted to actually do something that was pedagogical. So these are actual plots from the GPU gems chapter. This one right here, and the code is on Google Code, so you can read it all already.
So Lorena,
yes.
Does it make sense to try to use the direct method for smaller chunks and
of course,
combine
yes,
somehow?
that's the whole. That's the take-home message. If you have a smaller system, it makes sense. It accelerates.
No, I'm saying even for a big system, does it make sense to try to use the direct method for a lower level of the tree and then combine that with the higher level method?
Well, we do use the n square at the finest level of the tree.
So you already include that in the result?
Yes, yes. Okay. That is the P2P, okay. Particle to particle. It's always done at the finest level of the tree. We always have to do the n square evaluation, but it's done in such a small domain compared to the largest domain that it does not dominate on the complexity. So you must have, for example, a rather constant, a fixed number of particles in the finest box. Yep. So the number of boxes has to vary with n for the complexity of the algorithm to remain as you expected. Otherwise, what you see in the fast multiple method is as you increase n, if you don't switch levels to a finer one, at one point the n square starts dominating.
Yeah.
Right. So let me show you some results now, bioelectrostatic results.
Question from UCLA.
Go ahead.
Okay, on your slide 62, you are saying that you will do lot of local calculations on the fly, right?
This one.
So does it cause a lot of serialization? Those Legendre polynomial calculation?
Legendre polynomials are done on the fly. Sorry, I didn't catch entirely the question.
I mean, does it cause a lot of serialization in your programming?
Serialization. This is still done on the GPU. I'm not sure if I understand your question. No, I don't think that it causes any serialization. What it causes is that we're doing more operations. We do more flops than is done on the CPU to avoid global access to global memory. I'm not sure if I answered your question.
So you're repeating the calculation on each thread. Overall, you are saving time. Is that right?
Yes. Overall, one saves time because otherwise the transfer of data from global memory will start dominating. But means that on the GPU you're doing more operations, more flops than on the CPU.
Okay. Thanks.
For such technical questions, if you want to look at the code and post some questions there, I could probably get help from my postdoc and give you a much detailed answer if you want it. And the code, you can read the code, or we can point you to particular lines in the code and so on, because since it's all available, it's easy to do that. Okay, and we're happy to of course correspond if you want to look at the code and ask a specific question. So let me just show you some results at the end. I know we're quite short on time now. These are some results for the bioelectrostatics application. So the first one is, so I told you that in the continuum approximation we're going to represent the macromolecules as a continuum dielectric material with the addition of some point sources inside it at the locations of the atoms. So this picture simply is there to show you a lysozyme. This is an enzyme, and you have the shape of the molecule there in the sort of semi-transparent surface that is drawn, and the little dots inside represent the positions of the atoms. So this is to give you an idea of the size of the model of the molecule. Okay, we have 100,000 points for the representation of one lysozyme molecule, and then the result of our calculation is going to be the electrostatic charge on the surface using the boundary element method. Again, 100,000 points. And here is just some computational results. Now, I want to point out that these computational results are on the app itself, on an actual physically relevant calculation. And so it's not the ideal environment to do scaling plots. So this is not really a sort of methodical scaling result. I will show you some scaling results later with a more adequate problem. But I want to show you here that we have computational results for the actual app, and we see for this problem with number of panels on the surface varying from 31,000 up to 225,000. And we see that the fast multiple method is about 50 times faster than the direct here at the final n, which is 225,000. So FMM over direct, okay, 50 times faster. That's just the algorithmic improvement. Now this gap, I notice again, this gap will become bigger as n increases because FMM is order n and the direct is order n squared. So this is just one data point here indicating, you know, at this range of problem size, the sort of speed up, but it's not meaningful in terms of, I mean, it changes, right? So FMM is 50 times faster than direct at the final here on the CPU. On the GPU, the FMM becomes faster than the direct for n bigger than about 70,000. So remember the crossover point between FMM and direct moves to higher n on the GPU. The FMM on GPU is in this experiment 10 times faster than on the CPU. But I want to point out that this is on a highly tuned CPU code. Okay, the FMM CPU code that we're using here, you know, it's got the whole shebang of SSCs, instructions, and even a little bit of assembly black magic somewhere here and there to boot. So it is a very, it's got a lot of man hours in it. Okay, we didn't put all the man hours on the GPU side of things. Okay, it's a fair comparison. So it's a tenfold increase, which doesn't sound very impressive, but if you look at the absolute timings, it's a pretty good code. Then I showed you one lysozyme molecule, but it happens that molecules in a real biological environment are never on their own. Molecules are always in a crowded environment. So we imagine that you wanted to see how a molecule behaves in combination with, say, some drug or something in a real biological environment. You would have to have the solvent, the water, and perhaps you want to put a whole bunch of other molecules around it. So it's going to be in a crowded situation. Things change there. So here we have the possibility, thanks to the combination of the continuum model, the fast multiple method, and the GPU, the capacity to do 1,000 of these molecules in say, a certain random distribution inside a volume. These calculations we did in the GPU cluster of the Nagasaki Advanced Computing Center, which was built by Professor Tsuyoshi Hamada. Professor Hamada is one of the authors of the paper that won the prize performance category of the Gordon Bell Prize last year in 2009 with this particular cluster, the Dejima cluster. And you know, he kindly has given access, and we're collaborating with him in this work so that we were able to do some multi-GPU calculations of this problem in this cluster. I want to point out this is a hand-built cluster, and as you can see there, I have better pictures, but I thought that one gives you the idea of the situation. And here are some results with multi-GPUs for this problem, the lysozyme array of particles. So molecules. So we have these results in terms of scalability are kind of hard to read, but this gives you the exact timings, okay? And so we're looking at, you know, with up to 512 GPUs and billion, in the order of billion unknowns. And here's the largest calculation that was performed. 10,000 of these molecules. Each molecule, remember, is discretized with a boundary element representation of 100,000 boundary elements. Okay, so each surface has 100,000 panels, and we have 10,000 of these guys. And that system has more than 20 million atoms. The atoms are inside each of their molecules, and 1 billion unknowns, and the one evaluation of the whole electrostatics field was obtained in 1 minute on 512 nodes. 1 minute, that's the FMM evaluation. Now the FMM evaluation is done inside a GMRES solver, so that's why it says per iteration. We're accelerating the dense matrix vector multiplication that exists inside the GMRES solver, so we have to do many iterations of that one, okay? So 1 minute per iteration on 512 nodes, but we get a result, converged result in about 30 iterations. So that's the largest calculation. This